Howdy, AP PreCal, it's Miss Kosh. Today I am working through the 3/8 notes on the tangent function from Mr. Passwater. So he has made his notes available, and I thought I would talk through them for those of you who are using his notes. I've already taught this in my class, but I think he's got some neat ways of saying things. So once again, I haven't really worked through the problems, so you get to watch me think in real time. So they were talking about how we've already learned that tangent is the slope of the terminal ray, the terminal side of this angle. And so when we, so tangent, it's sine over cosine, which becomes hugely important when we get into doing trig identities. So that's what my kids are currently working on, but anyway, here we go. So tangent is the slope, tangent is that y value over the x value. So he talks about, let's look at the slope of the terminal ray as our angle increases from 0 to pi over 2. What we're looking at here is this has a slope of 0. And this, in this, if I came up to here, this slope is undefined. And then somewhere along the way, the slope gets more and more, so this slope gets more and more positive as we move our way through the circle. And the ones that we care about, he didn't label, but that's what's happening. So how did we say this? When theta equals 0, the slope of the terminal ray is 0, the first circle. As it increases, the slope also increases. As theta approaches pi over 2, the slope gets steeper and steeper, more and more positive. And then when theta equals pi over 2, the terminal ray is now vertical. The slope of a vertical line is undefined. See, if I had read ahead, I would have known that that was coming. All right. We can see now that when we say the slope is undefined, it is because it is infinite. The limit as theta goes to pi over 2 from the left, so coming, when we start to graph this, we're going to end up having an asymptote here at pi over 2. This would be when x, or theta, we'll call it theta, is equal to pi over 2. We're going to start approaching positive infinity. So we're going to look and see that here's from theta equals 0 to theta equals pi over 2. At 0, we had a slope of 0, and then our tangent value increased. So here is a little piece of the graph of tangent of theta as we go from 0 to pi over 2. Okay, and now they're saying, well, what happens between pi over 2 and pi? Well, pi over 2, we now have a very steep negative slope, and then it gets less and less steep as we get closer and closer to 0. A slope of 0 so right here, this would be like saying this ray, we're saying tangent of pi is equal to 0. So from pi over 2 to pi, we can see that slope transitions from negative infinity. So it's ridiculously steep, but in the negative direction. And that would be, so here is pi over 2. We can't have, and then this is that pi value that we just wrote down where I said tangent of pi is equal to 0. And so it's going to go down to negative infinity in that direction. So it's going to look something like that. So we're ridiculously steep, but in the negative direction, and then it gets less and less steep, and then it becomes a slope of 0 at pi. Okay, let's see. This is not how I usually teach that, so that's kind of fun. If you're curious to see how I teach it, go look through my videos. Okay, as we continue from pi to 3 pi over 2, then we're saying, so here we had a slope of 0, and then it's a positive slope, but it's small, and it gets bigger and bigger and bigger and bigger until it becomes undefined here. So this, if I came back to this graph, we're now saying we have an asymptote. I should have planned and given myself space. That lovely dotted line is going to be when theta is equal to 3 pi over 2, and so it's going to shoot off and go to positive infinity over there. Okay, key concept. Each time that the terminal ray is vertical, the slopes are undefined. When we graph the tangent function, that means we will see blank blank when vertical asymptotes. But that seems reasonable to me. Each half turn around the circle, we create another vertical asymptote. That is what he wanted. Okay, each half turn around the circle will create another vertical asymptote. So they're showing us what we graphed a second ago was we went from 0 to, here we put in a dotted, we put in the asymptote at pi over 2, so here's comparing what we just did and here. And then we had another 0 at pi over 2. So we graphed from here to 3 pi over 2 is what I had done with you. And so this, you'll notice this distance, everything that happens for the tangent function repeats between every set of asymptotes. So the period here from negative pi over 2 to pi over 2 is pi. Or you could say, okay, how far am I going from here to here? Notice I'm at 0, I go up, I'm down a negative, and I come back up to 0. This is also pi units apart. So we will discover that that tangent the parent function of tangent has a period of pi. So then when we start looking at transformations, the period is no longer 2 pi over b like with sine and cosine that we already saw, but it's pi over b. And the vertical dilation, this A is going to stretch things and pull it apart this way. I particularly don't find A all that exciting because I only require my students to show me where the inflection point is and to show me where the asymptotes are. And so the bare minimum that I want to see is 1, 2, 3 things. Or you could show me 1, 2, and 3 could be your next inflection point. So because I don't really care what happens in the middle here, I don't usually change the A value because, like, if I made A 2, then now we're going through this point here and this point here. Okay, that's cool. It's not the same graph, but it has the same basic shape. However, not every teacher is like me, for better or for worse. So we do have this point pi over 2, 1, and then negative. Did I say pi over 2? That's wrong. Pi over 4, 1. So if you think about it on your unit circle, the pi over 4 family gives you slopes of 1 and negative 1. So here at pi over 4, we could say tangent at pi over 4 is equal to positive 1. This is 5 pi over 4. That's also a positive 1. Notice it's the same line. This is the tangent of 3 pi over 4, and anything coterminal to it is negative 1. And tangent of 7 pi over 4 is negative 1. So if your teacher requires you to plot more points, the pi over 4 family, or halfway between the inflection point and the asymptote, is going to be pi over 4, 1. Or now, once you start doing transformations, that can change and shift and whatever. But this will always be halfway through, and then if it gets stretched vertically, you can deal with that later. For better or for worse, I don't always make my kids do that. Okay, so then we can shift it left and right with the C value. So if it's a plus C, then you're actually moving to the left. The vertical translation, we're going up D, or whatever that one is. Okay, let's see. A portion of the function f is shown above. The function f can be written as this. Okay, so there's no shift left or right, which we can tell it's going through 0, 0. Where A, B, and D are constants. Oh, he did change the value of... well, did he change it? Maybe not. Okay, let's see what we can tell. See, this is why I don't like changing A particularly. When I write a problem, I make A either positive or negative 1 and just kind of move on with my life. Okay, so here's what I noticed. Now we have a period. The asymptotes going from negative pi over 4 to positive pi over 4 are pi over 2 apart. And so that tells me that pi over 2 is going to be equal to pi over b, which means that our b value is equal to a positive 2. Could you see everything I was writing? Anyway, sorry. And then did I have a shift up or down? It doesn't look like it. This inflection point is still at 0, so my d value is still at 0. Notice that didn't shift up or down. And then it looks like, okay, halfway through, here's what I see. Halfway through right here, where do I hit? It looks like that's at 1, which means that I went halfway to the asymptote and I went up 1. That's going to give me just an A value. Here, I'll switch back. That's going to give me just an A value of positive 1. So I would say this is the equation. F of x is equal to tangent of 2x. Is that it? Looks like it to me. I would expect you guys to figure out an A value. If I want you to find a different A value besides 1 or negative 1, I would label another point and make it very clear what's happening. Super. Okay, the function h is defined as that. What's the period? Well, the b value is what affects the period, so the period is pi over 2. If I gave you a question like this, you should say thank you, because that should be pretty straightforward. Okay, let g be the function defined by this, which the following gives the vertical asymptotes. Okay, this is how I like to, well, so what we have here, basically our vertical asymptotes have been stretched by a factor of 3. So they had been at pi over 2, and then and negative pi over 2. And so then when I stretch them, they're now at 3 pi over 2 and negative 3 pi over 2. But there's a nicer way to do this. This is going to be a vertical stretch. This is going to shift everything down 1. So these things, the 2 and the negative 1, have nothing to do with my asymptotes. But the x over 3 does. So what I like to do is I say, well, where does the parent function have asymptotes? When I have y equals tangent of x, the asymptotes are when x is equal to pi over 2 plus they're a period apart, so they're pi k. So pi over 2 plus pi k. So I can do x over 3 is equal to where my original asymptotes were. And then I can solve for x. So multiply everybody by 3. I get x is equal to 3 pi over 2 plus 3 pi k. And let's see, is that an answer choice? Sure is. Actually, I disagree with constant. What it should be is it should be where k is an integer. So tweak that. Anyway, that was fun. Okay. Oh, no, there's more. How long have I gone? 11 minutes? Oh, I'll just finish this. You can watch a little longer video today, I reckon. Okay, so look at this. They are now 2 pi apart. So I have that pi over b is equal to 2 pi. And so I can multiply and say pi is equal to 2 pi b. Divide by 2 pi. I have 1/2 is equal to b. So that eliminates those two possibilities. And then I can see that I shifted down. My inflection point is now down, and so that tells me it's this value, or that equation. Okay. Here's on the unit circle. So what I like to think of as slope. And when we work through these, the values that we care about, go back and watch my other video. We have a slope here of 0. This is a slope, well, this one is the slope of 1. This is an undefined slope. And then what happens is you get root 3 is steeper than root 3 over 3. And if you're like, Ms. Kosh, where in the world did you get those numbers? I have videos that can talk you through that. And for the sake of time in this video, I'm going to have you go look for that. Okay, so pi over 6 is this one. It's the less steep, so that's root 3 over 3. Pi over 4, tangent of pi over 4 is 1. Pi over 3 is more steep, so that's root 3. Tangent of 5 pi over 6, that's in quadrant 2, and it's less steep. So quadrant 2 makes it negative less steep, makes it root 3 over 3. Tangent of 4 pi over 3. 4 pi over 3 is where? Down in this quadrant. It is more steep, and it's positive, so it's root 3. 7 pi over 4 is in quadrant 4, and this is negative there, so it's negative 1. Eventually, you should get this fast. Tangent of 3 pi over 2 is right here. That is a vertical line. Its tangent is undefined. Tangent of pi is equal to 0. So pi right here, the slope was 0. Tangent of pi over 2 is also undefined. And that is the set of notes for the tangent stuff. Go practice, subscribe to my YouTube channel, and I'll see you later.